So now I'm going to move to and talk about in some details about convolutional networks. And these are essentially the couple type of networks that we will gonna refer to a lot during our discussion on graph neural networks. So I want to have some basis for this. So convolutional neural networks are composed of at least one layer that uses, instead of matrix multiplication that we see in our linear layers, it is using a convolution operation on input data. That is going to be applicable on grid-like inputs. So for instance, we have images that is defined on a 2D grid. You have each point in the image is just a pixel, right? And it has a point next to it into basically, or up and down from that point. And that pixel represents some values. That represents how dark, or some basically measure of its darkness or basically lightness. And it has some measure of its color. If it's a colored basically image, it has, for instance, 3 different channels. So red, green, and blue. With those, we have 3 very basically values for each pixel. So let's say that our data now is defined on a 2D grid. Similarly, we can have data on 1D grid as well. So for instance, audio. Audio is defined on the basically time axis. You have frequencies at each basically grid point. You go to the next grid, a different value for frequency, and you continue that for however basically many nodes, your grid points you have on your discretized time domain. So this is very helpful because when you have a linear layer, the problem is that you have a large matrix, right? But now you can, instead of having a large matrix, you can have a smaller filter which goes over your data. It slides over your data and it basically captures patterns on different basically parts of the your input grid, your input image, your input audio. And the idea is that it is sharing some parameters when it looks at different locations in that image. So it's more efficient, less number of parameters, and so on and so forth. So let's look at 2 cases that we're going to deal with. So convolution is defined as a function, as an operator on 2 functions. And we can think about 2 vectors in 1D as functions that are evaluated at some basically grid points. So we can say that some vector, base vector W, which is evaluated at some point 0, 1 until L1. And we have some data X, which is evaluated on some grid points 0 to n-1. So it's an n-dimensional vector. The other one is n-dimensional, L-dimensional. And I can write the convolution as this relation, as a sum between element-wise multiplication of that weight vector with my basically input data vector over different basically windows. So what that means, we can show it easily with an example. Let's say that I have this signal X and I have this weight W, and I want to find a convolution between these 2. So first thing is that I will take this and I will put it on the starting point of my function X, on my signal X, and I say that I find an element-wise multiplication of elements of these vector W and this vector X. So it is going to be 0 times 1, it's going to be 1, plus it is a sum over those. So it is going to be 1 times 2, it's going to be 2. So we sum those 2, it is going to be 2. And that's going to be my first index for the output of this convolution. Now, I can repeat that. Again, take this, slide it over in the second, right? I'm moving from m equals 0 to L-1, right? I'm sorry, I'm basically computing it for different i's, and then I'm putting on the second I, for instance. I'm saying that 1 times 1 equal 1, 2 times 2 equal 4, and then sum of this is going to give me 5. And then I can continue that for every element that I have, and that's going to be give me a 5-dimensional output, 6-dimensional output, for instance, here. We can compute the dimensionality of the output based on our signal size and our window size. So now this idea can be extended to 2 dimensions as well. Now in 2 dimensions, we're assuming that we have a weight vector W, and we have some input signal, which can be, for instance, some image. We represent that with X, and we're saying that we want to find the convolution between these two. So again, let's start with an example. Let's say that this is our input signal, and this is the basically weights that we are using to compute the convolution in 2 dimensions. And we call this either weights or filter or kernel. There are multiple names for this in different, essentially, literature. So we take this, we put it on basically some starting points, 0 and 0. So we match basically the 0 and 0 and 0 and 0. And then I multiply these two element-wise. I'm going to say that this is going to be a sum between over 0, 1, 6, and 12, which is going to give me 19, right? So that's going to be the first element here. Then I'm going to move this, slide it over to this position, and then I'm going to again multiply these two element-wise, and that's going to give me 25. And then I'm going to just slide it over to on different basically places in our original signal, and that's going to give me an output for our convolution. So you can see that instead of having a larger matrix, I just define my model parameters now are how this filter is defined, how this kernel or weights are defined, right? So I have this input signal, and what I learn is these values in 4 values, and I'm going to slide that over on my data, and I'm going to capture some information. Now I can in each layer have more than one of these. I can, for instance, let's say that I have an RGB data, and this RGB data means that it's a colored image, right? So it has R's and G's and B's, essentially 3 graphs, grids. So I need to define 3 basically channels, 3 input channels, and I can define for each of those, I can define a different weight. I can learn a different weight for each of those. So it is not, we are not bound to a single input channel, right? So that's the scenario here. The last topic that I want to discuss is output unit. So we said that our model wants to learn a map from some input into some output. There are multiple, depending on our task that we're basically tackling, we have different types of outputs. If I want to have a regression problem, our output, we know that it is going to be some real value. If I want to have a 2-class classification, it is going to be one of 2 classes, which I can just show with a single probability of the event that basically that's being true, that variable being true. So, and I can have more than that, multi-class. We touched upon this a little bit before, but for a regression problem, we usually don't implement any nonlinearities. So why? Because these nonlinearities can restrict the flexibility of our model. Let's say that I have ReLU, which is giving basically a value between 0 and plus infinity, right? You can't have anything minus. Now, let's say that you want to solve some regression problem where your output is negative, right? So if you apply an outer layer, which is ReLU, it is, you're never going to get that negative value. So it is not appropriate to select something that is not going to give you the output that you are looking for. Or you can at the same time use sigmoid, and then sigmoid is going to give you something between 0 and 1. For regression, that's not necessarily the best option. So if you want to have real values as output, you just don't have any basically nonlinearities at the final layer. Sometimes you want to have some restrictions. So for instance, let's say that you want to compute some variance and you want to say that it should be positive. There's no way that my variance is not positive, but it's a real value. For instance, in that scenario, you can just apply some exponential at the end of the day so that you make sure that you're not, or you can find basically log of something. There are various basically numerical techniques you can use in order to enforce those type of constraints. So now let's say that we have a problem, which is a binary classification. In this problem, I'm only looking for the true event. I want to find the probability of the true event. And my model, right, is essentially a Bernoulli distribution. So when I use MLE, I want to fit a Bernoulli distribution and I want to maximize the probability of the true events that I observe in my observed data. So that means that I want to have a probability between 0 and 1, and I can use something like this. I can give it basically a maximum between, so I can first look at our linear layer. Let's say that this is some features that is coming from the layer before last. And that's gonna, using a linear transform, I'm gonna get some value and I'm applying some nonlinearity that puts it between 0 and 1. I say minimum of 1 and this, and then I get some variable. And I say that maximum of 0 and that variable. So that's going to always be between 0 and 1. There's no way it's out of that. But that's a problem to use this because we are depending on gradient-based methods, stochastic gradient descent in most cases to optimize our problem. And that's not going to give you a gradient, a good gradient outside of the basically the interval 0 and 1. So that's not really, so if something falls between the outside of that, you won't be able to optimize your model anymore. So that's not a proper thing to use. What we want to use, this is impractical, and what we want to use is something that is nice, smooth, it has values as we go outside of that basically interval, and we can use sigmoid function. Sigmoid function is a smooth function. It is basically between 0 and 1. We can control the smoothness with different parameters if we want. And it takes some input from -infinity to +infinity and returns some value between 1 and 0. As you go, it still has derivatives that can guide your optimization problem. So before, people used to use this for every hidden layer, but then they realized that if you basically get very large basically values in your hidden layers, that's not going to be good to use because they saturate at larger basically values anyways. So, but for the last layer in your binary classification problem, it is basically being used. So at the end of the day, what happens is that I will have a linear transformation of my features YL minus 1 using some weight W, and I get some output pre-activation ZL. And then I plug that into my sigmoid, and that's going to give me the output for my model. And last thing that we want to cover is the softmax function. So let's say that now we want to extend this Bernoulli distribution into multi-Bernoulli distribution. So we have multiple categories in our output. And what we can use, we touched on this before, we can use a softmax function, which takes some vector as input and rescales these basically values of your input to fall between 0 and 1. So such that sum of all those values is going to be 1. So you have different categories. Let's say that you have 5 different categories. It is going to give you a 5-dimensional vector, the layer before last. 5-dimensional vector that falls between -infinity and +infinity. The softmax takes this, it gives a vector of the same dimension, but this time they fall between 0 and 1, each of these, and they sum to 1. So just some summary of the models that we covered so far. We started from shallow embedding. We looked at the problems with shallow embedding, and we looked at why we want to even move forward with more sophisticated models as our encoder, or later we will see as our decoders. Now, the next, we said that we made some motivations for neural networks. We said that we can use neural networks in order to model more sophisticated mappings between some input and output. Then we looked at how we train these, right? Different approaches for training these. Then we looked at optimization models that were essentially trying to basically use some loss functions, some objective functions defined during training, and to optimize that in order to minimize or maximize that objective function. And usually we are just defining the loss function and we want to minimize that. So then we went over stochastic gradient descent, which is the most basically popular approach that we're using for finding parameters in deep neural networks. And after that, we went over backpropagation, which is a method to learn, basically find the derivatives that we need in the stochastic gradient descent, gradient of basically our objective function with respect to our model parameters that guides our optimization problem. We said that this backpropagation is based on chain rule of calculus. And then we used basically computational graphs to show how we can efficiently find how basically this chain rule should be constructed. And then we went over another type of networks, convolutional networks. We went over two cases, 1D and 2D convolutions that we can use for images and audio signals. And lastly, we looked at how our output units should look like based off of our basically the type of tasks in hand.